My name is Sherie Harding. I'm volunteer geologist for the Park City Museum. I've lived in Park City for 32 years and just recently have become very interested in the volcanics in our area. We have an era of explosive volcanoes in our geologic past. This is the way we were. This is actually an active volcano in the Philippines, Mount Pinatubo, and we have a fundamental principle in geology. That is, the present is the key to the past. If you want to understand the Keetley volcanics in Summit and Wasatch County, study active volcanoes. Study Mount Saint Helens. Study Mount Rainier. Study the conical mountainous volcanoes. Study Mount Fuji, and you'll have an understanding of what happened here. So this is the geologic story for Park City. Our landscape, Summit County, Wasatch County, dotted with volcanoes. And that's just 30 to 40 million years ago. These were the explosive volcanoes. For instance, here is a pyroclastic cloud, and this is the Mount Vesuvius Pompeii type destructive pyroclastic cloud. These are hot, they're full of ash, they're toxic gases, and you cannot outrun them. So I drove around Summit and Wasatch County and took some photographs. Here's a road cut on Highway 32 between Heber City and Francis, and take a look at it. There's big boulders in here. Over here there's laminated granular material. So I would take my students, my Geology 101 students, to this outcrop, and I'd ask them a simple question. Are these rocks igneous, metamorphic, or sedimentary? Well, it's kind of a trick question because, I mean, laminated particles, that kind of leads you to think it might be sedimentary. Well, you know the answer. These are igneous rocks. Their origin is that they were molten. Other outcrops exist around the county. Now, here's one of Keetley Volcanics at the Rock Cliff Nature Preserve. Oftentimes you will see these spires, erosional remnants. They're almost hoodoo looking. There's wonderful outcroppings of Keetley Volcanics in Silver Creek Canyon. That's on Interstate 80 as you're driving to Colville. And that's what the Keetley Volcanics look like today. Also, Keetley Volcanics underlie our geologic park. And I need to mention that you should probably take your children and grandchildren here because there's some homeschooling that can go on. There's 10 informative panels at this geologic park, and in the subsurface, Keetley Volcanics. So let's look at Mount Saint Helens. Not only do pyroclastic clouds come with these volcanic eruptions, but landslides or debris avalanches. And this was actually observed at Mount Saint Helens. You can see where all this material cut away and slid off of the mountain. This was triggered by earthquake, part of the eruption, but it can also happen just from over-steepening of slopes and gravity. So you can have, what you have is debris avalanche. Let's just pretend this is our volcano here in Summit County. There's evidence that material in debris avalanche slid all the way north, as much as 10 miles, in what must have been a cataclysmic event. So our geologist, Utah Geological Survey, Bob Beek, is recently remapping the geologic quad, Park City East, and came up with something new. It's one thing when geologists do work, they always have little tiny pieces of a puzzle where they have to put together the big picture. And that's what he did. So let's take a look at cross-section number 1. Here is our very own volcano. It has a name, the Park Premier Volcano. That's the one closest to us in Summit County. It's fed by molten rock, intrusive rock, and surrounded by layered sedimentary rock. Look at this dashed line. Okay, that marks the scarp that's left after this debris avalanche. So, cross-section number 2. 2/3 of 3/4 of the Park Premier volcano is gone, slid out to the north. And the evidence is in these 3 outcrops. That's what these oval greens are showing. And so Bob Beek appropriately named these outcrops the Silver Creek Chaos. And it looks chaotic. Here's a close-up of one of those green blobs. So here's the chaotic material that slid off of the Park Premier volcano. And the most interesting part is this clast right here is very old sedimentary rock. 300 million year old sedimentary rock, let's say 35 million year old Keetley volcanics debris avalanche. Geologists always like to take pictures of their hammer. They really like their hammers. So anyway, this was actually ripped up from the surrounding material when this debris avalanche happened on this volcano. So I'm introducing to you the stratigraphic section. Strata means layers, sedimentary rock, and from the Weber quartzite up to the Nugget Sandstone, those are the sedimentary rocks. I'm showing igneous rocks at the bottom, igneous rocks at the top, and they're much younger, 35 million years ago. Geologists show igneous rocks usually as the pinks and the reds. And over here is a stratigraphic section, and geologists show the igneous rocks as pluses or X's. So we have intrusive igneous rocks underneath the sedimentary rocks, extrusive sedimentary rocks, Keetley volcanics, on top of the sedimentary rocks. So I'm going to now talk about those sedimentary rocks, and I'll talk about them in terms of how they were back then when the sediments were being laid down, and what it looks like today when you encounter it when you're hiking and biking on the Wasatch back. Again, you're going to have to learn the stratigraphic section. Here we go. Weber quartzite, Park City Formation, Woodside Shale, Fanes, Ankara, Gartra Grit, Nugget, Twin Creeks. Okay, originally these are always laid down horizontally on a seafloor, riverbed. Well, they're not horizontal anymore. Here's a picture of the Wasatch back, just a sketch. And there's the strat section. Weber quartzite, Park City Formation, Woodside Shale, Fanes, Ankara, Nugget. And they're all tilted. So how did that happen? Let's start talking about these layers of rock. Starting at the bottom, the 300 million year old Weber quartzite. And geologists show it as a dot-to-dot pattern. This is an extremely well-cemented quartzite. Quartz sandstone well cemented into a quartzite. Back then, you may have heard of Pangea. This is the time when all the continents were coming together. And this red square with the bite taken out of it, that's Utah. Utah is half in and half out of the water. So what did it look like? We look at these Weber quartzites today and we go, ha-ha. Well, all I could come up with was the beautiful white sands of the Emerald Coast. This is a Pensacola beach. And the quartz sand is white, extremely well sorted, all the same size. Well, now they're extremely well cemented together. And if you're hiking up on Bald Mountain and you see these white rocks, and on a sunny day they'll sparkle, it's kind of a druzy sparkle that you'll get off of these rocks. And just think of the Emerald Coast and the Pensacola beach sand. They're probably, that was their origin. Now while I've got this picture up here, I need to point to a spot along Jordanelle Reservoir, right there. That is the location of the Park Premier volcano, what's left of it. And Bob Beek from Utah Geological Survey has volunteered to take us on a hike, museum people on a hike to the remnants of this volcano. So someday we'll get to do that if we ever get to hang out with each other. Anyway, moving on up section to the Park City Formation just 285 million years ago. Geologists will show this as a brick pattern because there's a lot of limestone in the Park City Formation. Well, what did it look like back then? I love to use these paleogeographic maps. Okay, here's Utah. This is subaerial. And then this is shallow water, deeper water across the state. And you will get thicker occurrences of the Park City Formation near Park City. And this is what a Permian seafloor would have looked like. We're still near the tropics. We are shallow seas, and that's a highly productive environment for life. And these are the kinds of critters that lived some 285 million years ago. What's it look like today? Here's a picture taken of Masonic Hill, and there are two different Park City trails that cross the outcrop of the Park City limestone. One of them's on the Lost Prospector Trail, another one, I think this is the Masonic Trail. Anyway, stop and take a look. I mean, I've not been able to find a lot of fossils in the Park City limestone. Shell hash, yes, but just think of that when you're walking over this particular outcrop. It's a little more technical section in the trail anyway. I have to stop at this point because at the top of the Permian, which is the top of the Park City limestone essentially, is a mass extinction. I marked it on our geologic time scale as a big black line because of all the mass extinctions in the last 500 million years, and there's been 5, we are in the 6th one, this one was the most dramatic. Here's Paleozoic, that's ancient life, Mesozoic, middle life, Cenozoic, more recent life. So it's quite a dynamic boundary in the record of life. It's called the Permo-Triassic mass extinction. 96% of the marine animals extinct. 70% of the land animals extinct. And what kind of critters were roaming around? That is the end of the age of amphibians and the beginning of the age of reptiles. So there were land animals, and 70% of them went extinct. Okay, that said, let's continue on up with our stratigraphic section. But what I want you to remember is that when you're out hiking and you step out of the Park City limestone and into the overlying Woodside Shale, you're stepping over an incredible time in the history of life on the planet. So the Woodside Shale, 250 million years ago, showed as dashed lines because it's siltstone, mudstone shale. Paleogeographic map. Utah still pretty much in the tropics and underwater. From shallow water, mudflats, this is kind of intertidal, to deeper water across the state. Ripple marks. This is one of those present, the key to the past. Ripple marks looked the same back then. Here's another back then. Go over to just off of Kearns Boulevard and take a picture of these ripples this is an exposure of the Woodside Shale. Perfect ripple marks, just like you see today in the intertidal. But what's different? Very few fossils. So I've lived here a long time, and I studied trace fossils, and I haven't found them in the Woodside Shale. But if you go to the beach, get in the intertidal, you're going to see snail trails, you're going to see tracks of crabs, you're going to see holes that crabs have made. I don't see those in the Woodside Shale. So, it must take a while for a life to recover after a mass extinction. Other places where you can see the outcropping of the Woodside Shale, here it's almost vertical. Bedding plains are almost vertical. It's on the Crest Trail. And if you see rock outcropping in the distance, it's thinly bedded and it's red, iron stained, you could probably venture, yeah, that might be the Woodside Shale. And you might be right. Geologists always hedge their bets anyway. Here's another section along the Crest Trail, and stop, get off your bike, look for fossils, because this is a really technical section. You probably shouldn't be riding it anyway. But that's Woodside Shale outcrop. Moving on up section, the Thames Formation 245 million years ago, and it has some limestone in it. Here's a picture of Thames Canyon. The Thames Formation is one of the softer rocks. It eroded away. Enough said. Thames Canyon. Moving on up section, Ankara Formation, and I'm going to spend a lot of time on the Gartra Grit because it is very well cemented and it's a marker bed around town. Originally, back then, there were braided streams, and they had to be covering much of the state because the Gartra Grit is an extensive formation. Here is water, and it's called a braided stream because the water coalesces and separates, and it's a high energy water system, so it's going to carry the larger particles. And here's an example. I took this photograph right across from the White Barn. And look at the size of this quartz pebble. And these are coarse sand grains, which means about 2 millimeters in diameter. And this is well cemented material. So well cemented that it is a cap rock on the north limb of, let's say, this Thames Canyon. So right here, that is an exposure of the Gartra Grit. And they've recently built one of their trails through it, the Mid-Mountain Trail, and that is certainly a dicey section of the trail when you're crossing that particular geologic unit. When you're entering Parley's Canyon, coming from Salt Lake, just take a quick glance off to the right and you'll see Suicide Rock. This is an erosional remnant of the Gartra Grit. Someone here trying to commit suicide, I think. Moving on up section, the Nugget Sandstone, just 200 million years old. Sandstone, dot-to-dot pattern. It's named Nugget. It's very hard, but it has nothing to do with gold nuggets. It's just well cemented. And this particular sandstone, let's look at the paleogeographic map. Utah is no longer underwater. It's covered with a vast desert. These black arcs are showing the leeward side of sand dunes. And if you go to southern Utah in the national parks, it's called the Navajo Formation down there. You will see petrified sand dunes is commonly what they will be called. So let's take a look at Sahara Desert. That's what we had here 200 million years ago. And if you follow a sand grain, which is on the windward side, bounces up the side of the dune, and then falls out of the wind and rolls down the steeper leeward side of the dune, this is the part that's preserved in the geologic record. Let's look at today. Picture taken at Red Ledges. Check out these thinly laminated layers of the Nugget Sandstone. That's the leeward side of a sand dune. So, there was an incredible journey that Utah took all the way from the tropics to now we're at 40 degrees north latitude. Maybe we were in the desert latitudes, because there was a vast desert here 200 million years ago. The Nugget Sandstone is used as a building stone commonly, and iconically it's Iron Mountain, one of the high points on the Wasatch Back, because it is so resistant to erosion. Okay, so we have all these nice horizontal layers of sedimentary rock. Well, if you're going to take a continent and move it all the way from the tropics to 40 degrees north latitude, there's a lot of compression, mountain building, orogenies is what they call them. And so there's tilting, folding, faulting, and anticlines that formed during this time. By definition, anticline is an upfold. So when you have a lot of compression and layers of sedimentary rock are at depth, they can deform plastically. So here's an upfold and an adjacent downfold. We'll call this an anticline. And I challenge you to try to see this huge geologic structure, even though 90% of it's eroded away. Okay, so imagine. Let's take a closer look right here at the north limb of this huge geologic structure. And the remnants are, there's a marker bed, the Gartra Grit, the Nugget Sandstone over here in Iron Mountain. So think of that as the north limb, and that's probably why all of your layers of sedimentary rock are tilted that way on the Wasatch Back. And the high points are determined by how resistant these rocks are to erosion. Flagstaff Mountain, Weber Quartzite, now that's resistant to erosion. Nugget Sandstone, Iron Mountain, underlain by a very resistant layer of rock. Now we're going to go into some three-dimensional geology. Right here, that's what we're looking at on the Wasatch Back. The limb of an anticline, everything's tilted. But if you're looking at top view, say you're up in a hot air balloon, you're looking down on Park City, when something is folded, then the fold is tilted, then it's eroded off, the pattern left on the ground is a horseshoe pattern. Let's see if you can see that. You're driving out of town, and let's back up a minute. You're driving on 224, and let's say you're going right down the axis of that fold. Just glance up to your left. That marker bed is pitching down towards you in your car as you're driving on 224. Now, glance up to your right. Here's the white outcrop, grayish white, of the Gartra Grit. There's the marker bed off to your right. Now as you drive on past the white barn, past the farm, these two connect underneath the highway in that horseshoe shape. So think of that as you're driving out of town. Even some geologists have trouble thinking in 3 dimension with these big structural features. So let's go back to 2 dimensions. All right, here's your stratigraphic section that you're familiar with, Weber Quartzite overlain by Park City Formation, and they're in the form of an upfold, been eroded off. But the most important thing I want you to see in this slide is these vertical lines, dashed, sometimes solid. Those are the faults. There's a lot of faults, a lot of fractures in these rocks around Park City, and they're famous faults. I'll read some of the names. The East Crescent Fault, the Frog Valley Fault, the Silver Fault, the Hawkeye-McHenry Fault Zone. Now they're famous because they were very productive silver mines. So back to our igneous rocks, the intrusive igneous rocks that came in underneath the stratigraphic section. The igneous rocks spewed out of the volcanoes as the Keetley volcanics on top of the stratigraphic section. And how did they get here? That's the source of the precious metals. Oh, what's that picture? Okay, geologists, this is a geologic map, will use colors to indicate which rocks are outcropping on the surface. The ones I want you to focus on are the ones that are pink and red and orange. Right here and here and here. So this is a map showing the Wasatch Front, the Uinta Mountains, and they actually tee into each other, and then the extension across the Salt Lake Valley into Rio Tinto, okay, Kennecott Copper. That's the Wasatch Igneous Belt. So these igneous bodies came to rest at, maybe it was a zone of weakness, but that's where they are, and that's the source of our precious metals. So let's talk about that process of separating out these precious metals. This slide, the mineralization process, I'm going to start with a very large scale and circle around to just a 100-meter scale, 5-meter scale, 10-centimeter scale. So what I'm showing here, they look like hot air balloons. They're actually plumes of magma, maybe sourced as deep as the mantle, and they're making their way very slowly up through the lithosphere. And during that time, things happen inside of these bodies of magma. Some minerals crystallize at a high temperature. They crystallize early and they settle to the bottom. There's a lot of water associated with these bodies of magma, and the water just gets more concentrated and rises to the top, and that's what's shown in picture number 2. There's a veneer around the edge of this body of magma. This is hot water, and it carries SiO2, which is the formula for quartz, and it carries silver, lead, zinc. So Mother Nature is doing a natural process of separating out some of the precious metals from this huge body of magma. Let's take a closer look, because here's this little finger. You've got water under pressure, and it's hot, and it's squirting out into the surrounding cracks of the sedimentary rocks. Here's one of them. So it's showing hydrothermal solutions in the crack, some of them squirting out into the bedding planes of these sedimentary rocks in Park City. And this is where the squares are showing the precious metals. This is where the precious metals actually get deposited, associated with these fractures. And so here's a schematic of, I'm just showing 2 of our mines, famous ones. Again, you can see our stratigraphic section and the fold in the subsurface, igneous rock, and here's a fracture that's been filled with hydrothermal solutions that have precipitated some of our precious metals. And that's the just rough geologic description of Ontario Mine. Silver King Mine, another crack fill lode deposit, and then the Park City limestone was dissolved away by these hot, very caustic solutions. This is called the Jenny bed, and you can see how it gets deeper and deeper. They mined it as deep as they could. Maybe there's more down here, and maybe we'll never know. The definition of a Bonanza deposit, that is what I'm showing in red right here, at the base of the weathering zone. Now, these have been in place long before the prospector showed up. There's been time for weathering, erosion, and leaching to the base of the weathering zone. So one can mine through the weathering zone and then get to a zone where it's twice the concentration of metals, silver, lead, zinc, and that's a Bonanza deposit. I'm calling this granitic. That's a igneous rock, form of igneous rock in the subsurface. I wanted to show this picture because if you read a story in Treasure Mountain Home, the subsurface geology really did not cooperate with what the prospectors were doing on the surface. So here's a cross section. This is the surface of the earth. Empire Canyon, that area. And this red line marks a claim boundary. Prospector set this and he figures his claim goes all the way to China. And here's another claim boundary. Yep, straight down. Well, this mineralization, shown as these black squares, follows the faults. It doesn't really cooperate with the claim boundaries. So there was an opportunity for lawyers to make a lot of money here as well. What's happening today geologically? Well, we had compression over the geologic past. Now it's quite the opposite. Tectonic extension. All the way from the Sierra Nevada mountains, all the way across Nevada to the Wasatch Front, Wasatch Fault, to the Wasatch Back. The crust is stretching. You might not notice it. Things happen slowly. You might notice mining, skiing, development. A lot of that's happening. What I'd like you to take away from this talk: when you're stuck in traffic, you're driving in on 248, look at the Wasatch Back, pick out your marker beds. Picture the limb of that large fold, the remnants of it. Learn your stratigraphic section. I came up with this mnemonic, top down. To connect nationwide, agree to watch Park City, welcome the world. If you memorize that and you're walking along on the Crest Trail, for instance, that's where if you start at Empire Pass or Guardsman Pass and you start walking north, you're going to walk through the entire stratigraphic section. And it'd be interesting to pick them out. By the way, this little V is showing Empire Canyon. I have to warn you, if you hike up Empire Canyon, you're going to be in the Weber quartzite, but it's not white. It's iron stained, it's been affected by those hydrothermal solutions, but you can still recognize it. Highly fractured, highly iron stained, and that's associated with the deposition of these minerals. So you can make your way along the Crest Trail and get through the entire stratigraphic section. I'd like to thank the Sunrise Rotary who put together the geologic park. There were not only contributions of finances, but I'd say a lot of contributions of knowledge went into this geologic park. And I'd like to thank people from the museum and also Sam, my videographer. Thank you very much. And that's all.